So, hello Rahul, welcome to the interview. So, before starting off, you can just give a small introduction about yourself and why you decided to appear for this interview.
Right, so I'm Rahul, and I'm a recent CSE graduate from SRM Ghaziabad, and I've been preparing for for the entry level role for software development engineer in big MNCs, and I just wanted to see where I stand in the water, so that's why I'm here for this mock interview.
All right. So, Rahul, I think that's the right thing to do to testing yourself. And since you want to test yourself, I will actually I would like to let you know that the whole interview is based around how the questions are asked in Amazon, right? So we can start off with the first problem right away. Let me just paste the prompt statement in the code editor and let me know if you have any questions.
Right, all right, I can see the problem. I'll just take a minute to read it.
Yeah, sure.
Right, so I'll just restate the problem.
Yeah.
So essentially, there are n number of potted flower plants that are given to us. They are numbered from 1 to n, that is the number of total plants there are, and some k people walk along and they water a given range of labeled plants, and at the end we have to return like the final number of times for each plant that it was watered, right?
Yeah, that sounds good.
All right, so I'll just take a quick second to arrange my thoughts. Uh, can you give me the range that this for this question the n or n and k can be?
You can assume n and k to be at max 10 to power 5.
All right. No.
Yeah. Yes, also please let me know what you have thought so far.
All right. So since the number of the maximum number of values that it can be 10 to the power 5, I think we have to do the solution in a linear fashion. Like we could only iterate over this plants, or should I say the range of the people that we are given to us with the ranges of watering the plants. I think we can only iterate over it once, or we can iterate over it multiple times, but in parallel fashion, so as to say that we don't go into some n square complexity.
All right.
So I'm just trying to come up with a way to which we can arrange the number of time a plant was watered according to this, like in this fashion. Okay, so uh, one question is the range that is given to us, is it like in some, is there any order to it?
No, there's no order to it. For in the sample test is here, it might appear that we have an order, but obviously the range order does not matter.
Right, right, right. So one way that comes up to my mind, I think we could like try with some sort of linear fashion, linear iteration over the range. So how can we do that? First of all, I think we do need some order to it. So it's essentially, I think we need the all the uh, left pointers of the ranges in ascending order per se. I think we can do that easily by using a heap. I think a heap can we can just like push all these ranges into a heap, and that will only take care of it. It will arrange all the ranges according to the value of the left, and if the left is same, they will look to the right. So that way the we actually arrive at a order to all these ranges, right?
Okay.
So uh, next what we can do is we can devise an algorithm that actually uh, basically goes over the each plant only once, and just uh, basically okay, so how do we do that? Let me just take a pen and paper and formulate my thoughts.
So just to help you out, the let's say if even if we do not, I guess you're on the right track. You should devise an algorithm which should uh, keep the track of how many times a particular plant has been updated in a linear fashion, right? From if you go from left to right, you should have an update of for that. But yeah, I don't think unless you will have to necessarily sort the ranges. Yeah, it might give you some kind of uh, pattern here, but it's not ultimately necessary, right? I would like you to think along the lines where let's say for a range L comma R, right? So can you devise an algorithm which is in linear fashion where you do an update, right? You do an update, but later on after that particular range, let's say you have to remove that update as well. For example, let's say I decide that okay, from this point L, I'll have to increment the count of the water plant by one, right? But after some point, you have to cancel that effect as well because it will keep on adding to other plants, right?
Right.
So I want you to think along those lines.
A few approaches come to my mind. I think we could somehow, like if we were to use a heap in this case, like we could just like, uh, as we have already sorted this, we could just iterate over the plants from index 0 to n, and for each range that you are given, like basically we pop the top part of the heap. We do this for till all the heap is empty. And so basically, first of all, the range that comes out is 1 and 10, and then we can do another while loop inside this range, basically till the heap is empty, and till the till the next left pointer is basically it's inside the right pointer of the above thing, right?
All right.
So that way we know that the L to L part basically gets updated the default value when we pop this, and that default is always like a range will always start with a value of 1. So we do that, we do L to basically this is L1, right? So this is the top part that we just popped, and this is the L2. We do a for loop till L1 to L2, and we update it by start value. And after that we know that L1 and L2 won't ever be encountered in future because we sorted this in advance. And then we can reiterate, we can push a new range onto the heap, that is basically uh, a range from L2 plus 1, L2 plus 1 till L2 plus 1 till the R2. No, it should be R1. So basically R1, and we actually don't ever pop this, since this was just done till the top part gets satisfied. So we essentially we have just uh, gone over the first range that was there, and we have moved thus far till does that a valid range that is basically we are done with a certain range that we won't ever have to
All
do it
right,
again in
Rahul,
the future.
I have a counter question for this. Let's say
Right.
I gave you eight. Let's say I gave you eight ranges, right? And all of
Mhm.
them are 1, 10. All of them are 1, 10. So I think according to your algorithm, it at worst it will run n square times, because for, let's say for L1, for your first range 1, 10, it will look for another range which is also 1, 10, right? So all of the other n minus 1 ranges are 1, 10, so it kind of form a n square kind of loop. Does that make sense?
I don't think it will do a n square, because that n square would have been 10 to the power square, that is 100 times. I think at each step it would just go over one, like let's just say you formed a uh, that is 1 comma 10, right? And this is given by 1 comma 10, 1 comma 10. Like just let's just assume that it was 3 times in this case. It would be 1 comma 3 for ease, and the n square part should be around 9 times. But as we go over this range, L1 becomes 1, and L2 R1 becomes 3, and we go inside the loop again, and we see that L2 is also 1, and R2 was also 3.
All
So
right.
we update this range till 1 and 1, and we like push it again. So at max I think it will just like increment at each stage till 1 by 1. Basically the next range will, that we push again is 2 comma 3, and last range we will push is 3 comma 3. I think it's a linear solution only.
Mm,
I think we will be pushing only one extra range each time,
okay.
each time on the heap as well.
But that's what I'm saying. So if you're saying that we will not iterate through 1 till 3 again and again,
Right.
so how does
So
that
basically, first
track
of all, we
the
arrive
updates?
at basically this is the first while loop, right? So this is the first while loop, and then we do this till the queue is empty, and we go into again, and we arrange another one again loop here, that is while queue. So basically, we do while queue, and the top part is actually like the L2 L2 is less than L1.
Okay.
If this case satisfies basically, so like I don't think it should be a if loop, it should be a if loop. And I think the while was a statutory thing. We don't actually need it, since we can just pass along a valid array, and we could just do a for loop here right now. I think that will make more sense to you, that way it's a linear, like we can do that. So basically if L2 is lesser than uh, if L2 is lesser than R1, that is the case here, because L2 is given as 1 and L3 is given as 3.
All
So
right.
we know that there's a start here, right? So there's a start here that is 1, and we keep that start. We have to increment till L1. Basically we form a range that is the range where they don't overlap, right? If that makes sense. They for a range where they don't overlap.
Okay, can you just quickly dry run for the above test case so that we know it works? So
Right.
then we can move on
So
to the code.
right. So here we go. It's first of all we arrange this in a linear fashion. That will be 1 comma 10. That will be 2 comma 2, and so on. Basically, I think yeah, it's already in a sorted fashion only. You don't need to sort it. So first of all, we arrive at 1 comma 10, and then we check the next range is 2 comma 2, and so we iterate till 2, and we update for the first. I'll just maintain the array, the watered array right here. It will be 0 for all these cases, so basically 10 plants, or should I say 1 2 3 4 5 6 7 8 9 10, that's 10 plants. 5 6 7 8 9 10, right?
All right.
So we arrive at 2 comma 2, and we see that it is lesser than that, but we make a valid range that goes 1 till 2 to include it. So basically we iterate till 2 and we update it by 1, right? So we update it by 1, but we also, for the second part, now we update this by 1, and we push a range on top of the queue. That range is basically that range will be 2 comma 10, right? How that makes sense. So basically we isolated a range that was not overlapping, and we excluded it, and we appended all the values, and we push another the next range that will be that we have not encountered yet,
All
that we
right.
have not done for the watering yet.
All right.
So basically this heap will become, this will get popped out, this will become 2 comma 10.
All right.
So the top becomes 2 comma 2, and here we get 2 comma 10. So now for this case, this actually is a valid thing. So basically we don't actually have to isolate anything, we can just update this range and we can just pop it. So basically 2 comma 2 becomes 2, and we go pop out, so this heap value also gets popped. Now again we do this for 2 10, and we arrive at 3 comma 3, and this just keeps on repeating. Basically we again, like, we append 1 to this range, and we append a new heap value that is 3 comma 10 here, and then we update 3 again. So basically, oh my bad, this should be 2, and we go till all the way down till basically this becomes 9 and 10, right? So basically all these value becomes 2 comma 2 comma 2 comma 2,
All right.
and for the last range it becomes 1 comma 1.
All right, Rahul. I think this seems fine to me. Can you just quickly tell me the space and time complexity for this solution?
Right, so if we count the array that we have to return, the space complexity will again become O of n, though we also have to maintain a queue, but the range is given in the k, so it kind of becomes O of n plus k, but since both of are equal, we can assume that it is 2n, and that is basically comes out as n. And for the time complexity thing, I think it is again a linear, only because for the time it takes to sort all these ranges, that is n, basically heapifying the array. And lastly, for iterating over these ranges, it is slightly above n, but it's still linear, so I think we can just take it as O of n.
There's no log factor since we are sorting in a heap.
All right, so you are talking about the default functions complexity that we have to take in account.
Yeah.
So yeah, I think, yeah, you are correct that because popping any value from a top of heap takes log n, and we basically we pop a total of n times, so that becomes n log n. I think you're correct there.
Okay.
My bad.
All right, Rahul. We can go ahead and start coding the solution.
Should I create a new file for this?
Yeah, you can create a new Python file if you want.
Right, is there any boilerplate that we have to do this?
You can just create a initial function by yourself, take in and
Right.
the inputs
Alright.
and nk and the ranges. You can have a vector of ranges as input.
Yeah, all right, that works. So I'll just start by creating a function. I will just I will just call this basically, first of all, let me just import the necessary file that I will be taking, right? So I can just import heapq as the default heapify function for Python. And next, I think I'll just call my function, what do I call it? So we are watering plants. We have to return number of times the plant watered. So water plants. I'll just call it water plants, and I will take in account of n, and n is an integer, k is also an integer, and basically the range. So watering, I'll just call this watering, or I'll just call this water, and that is a list of integer. And finally I have to return integer, right? So basically, first of all, let's just initialize a priority queue. We will initialize this only, and next up, basically, first of all, the range that is provided to us, we have to convert it in heap, right? So heapify our watering list. So that is pretty easy actually. I think since it is a list that is given to us, we could simply call this pq heap q dot heapify, and we okay, so yeah, we can just pass water itself because it will return a new list itself, right? So we don't actually have to copy anything.
All right.
It will assign the new list to us. Oh no, on the second hand, I think we can do it a more robust way. That is by copying, first of all, copying the water, and thus we create a new instance of it, and we can call heapify right here. Basically, we heapify the queue, right?
Okay.
So now what do? We have to iterate over this heap and isolate a range that is to be watered right now, right? So we do the watering pass, and first of all, I think we can also initialize our list that is 0, the number of times of n, so that n is the number of plants. Yeah, that makes sense. So we do this while pq is present, and first of all we pop the top part, so we can call this L1 and R1, that is heap q dot heap pop, and we just pass heap q to it, give priority q to it, right? So all right, so now we have to check if the top part, if the, so we can again initialize our new variables. We can call this top, so how do we do that? All right, 0 0 2. Since heap q is naturally arranging all the necessary uh, necessary ranges in a minimum heap queue pattern, we can just check the top part of the heap queue, that is pq dot 0. And first of all, for left part we could just check for the 0 part, and for right part we could just check the next part. And if L1, if L2 is actually lesser than L1, so basically this is the case where we isolate the ranges, right? So we assign the new range now. So basically we know that there is an overlap there. So first of all, we go for here water amount, that is 1, and if L2 is less than L1, we basically create a new range, right? So first of all, watering range, uh, so I can call this another thing, I can call this water 1 and water 2. Basically this is, I will initialize the range as to this range as to L1 and R1. Basically this is the default range that we have to water, right?
Okay.
So if a new range appears, basically if there is an overlap, we we isolate the new range. So the R1 with the water 2, basically the end of the part where we have to water, it becomes minimum of R1 and L2. Basically, actually it is always lesser than, so we can just call this L2. And basically we have to push a new range on top of the heap, right? So we do a heap q dot heap push or top of pq, and this range is actually L2 till R1, right? So this is a new range that we are pushing on top of it. And now we have to water all these plants that we have extracted. So we just go for I in range w2, and for the highest amount we just increase the water amount, right? And lastly, I think we are yeah, so okay, so we are popping we are recording the variables, we are assigning the water variables, we are pushing the new amount. Yeah. So lastly, we can just return result, and I think this is the final answer. Yeah.
All right. Okay. So can you do a dry run on a small test case of your choice, or you can just do a dry run on the test case given to you?
All right. So I'll just take my previous test case that you had provided, like this, the problematic case, right case, right? So we can just call it right here. So the priority queue actually becomes, uh, yeah. So it becomes 1,3, and for the next part, we basically append this queue to that part, right? So basically, our result, it stays 0, 0, 0. And for the first part, we pop the first element. So basically, L1 and L2 becomes 1, 1, 3, and water 1 becomes water 2 becomes 1, 3. And for this range, we actually check that, and yeah, so we arrive at a situation where we actually have to water. So basically, water 1 and water 2 are updated to make water 2 exactly equal to L2. That is, uh, this was R1. If this is R1, so basically, next part what we have to do is uh, L2 and R2, that becomes 1, 3 again. So W2 becomes 1, and we water the first plant, and we append a new priority, new range of the priority queue that is given by 2, 3. Actually, this will become 2, 3, and the top part is this remains 1, 3, right? So again, we arrive at the situation, and now we will water till 1, 2. So this will become 2, this will become 1, and again, so this range becomes 2, 3, there is 3, 3. And lastly, we will water this part again. So we increment this 3, we increment this 2, and lastly we'll increment this 2, we'll increment this to 3, and lastly one range only remains, that is 3, 3, and this becomes also 3.
So, but you did not update your priority while you're doing the dry run. So will 1, 3 and 3, 3 remain in the list?
Right, I was actually worried about the time for the second question.
Right, I guess, yeah, we're pretty close to a time, but yeah, I guess I can give you a few extra minutes for this.
All right, so okay, so I can do that, sure, for sure. I can
I just
again.
wanted to know if you would pop those elements or not. So makes sense.
Okay, so we can just start from the beginning. I think that's easier. Mm, I don't know where we lost the track. So again, so basically this becomes 1, 3, and water 1, water 2 is as well 1, 3 right here. So first case, we arrive at this case. So water 1, 2, water becomes 2. So that we arrange it to 1, and we water this part, and we append a new. Basically, we have to pop this initially, right? So we had popped this, and we arrive at append a new range to it. That is 2, 3, and now the watering part has become this. So we arrive at the new range, that is 2, 3, and this L2 part becomes 2. So for the next part, the water range has to become 2. So we water we had popped this right now, and we the new range, I will just append the new range right here, which is L2 R1. So this is what we are appending if we arrive at collision, right? So just to make sure you can follow up.
Okay.
Okay, so now we have arrived at 1, 2. So we water 1 again, we water 2 for once, and now we have to append L2 R1. L2 is given by 2, and R1 is given by 3. So we actually here we update this L2 to 3 again. So this becomes 3, 3. So we move ahead. No. Oh, so we were at the first index only, so this stays at 2, right? All right. So now we come at 1 comma 3, and we see that our next watering parts is right now it's 1 comma 3, but the next part is 2 comma 3. So we update this part, and with uh, the L2 becomes 2 again, and we water till the last part. So this becomes 3, this becomes 2, this becomes 1, and we have to update our new range. That is basically we had popped this right now, right? We had popped this, and now we append a new range that is 3 comma 3. Lastly, we arrive at 2 comma 3. So this time this is 2 comma 3, and water 1 and water 2 is 2 comma 3, but and since we arrive at a collision again, so this becomes 3 comma 3. So we pop this, and we append one extra 3 comma 3 right here, and we have watered it once again. And lastly, these two ranges don't actually collide, but they end up watering the same point twice, so this becomes 3. If that makes sense, we pop this, and it's just go ahead and water this
Okay,
twice.
that seems good. And anything last you would like to add? Yeah,
But Edward?
like you would like to add anything at last?
No, I think that's all.
Okay. Hmm. We can move on to the second question now.
Right.
So let me paste the second question at the bottom of the same text file that we were at earlier, if that's fine. Okay, this one is an interesting problem, Rahul. So I would like you to carefully read the problem statement and let me know. After
All
that,
right, I'll just take a minute.
please let me know if you're able to see the problem statement. It's at the bottom.
All right, so let me just restate this problem once with you.
All right.
So basically, there is a starting point position for the prisoner that we are impersonating. So he starts running in some position, and but there are also other guards present. I'm assuming all the guards can also just move on in the empty cells, right? They can't pace through walls or something like that.
They cannot run into empty cells. Yeah. They cannot run through walls. Yeah.
Yeah, that's fair. So basically, we have to reach guard can that is reach a boundary cell. By boundary cell, what do we mean by boundary cell? So is it a wall? It can be a wall, right?
Uh, Boundary cell
Like,
is basically yeah, we can contain that. Okay, we cannot go outside a particular size of this grid, right?
okay,
That's all you have to take in consideration, that you cannot run outside the boundary of the grid.
okay. So, mm, so any opening that lies on the boundary of the
Yeah,
that is
that's an
considered.
exit. Yeah, that's considered. For example,
That's
here.
exit. So we have to reach an exit, right? So the prisoner is actually trying to escape this matrix, and it can run, and it has to avoid by the guard at any stage. So it's like a kind of a complex problem because the guard is also moving. So we have to cater for the worst case where the guard can intercept this prisoner, right?
Yes. So ideally, you have to think along the line. Okay, the guards are mm, playing in the best manner possible in
Right,
order to solve, in order to stop the prisoner. So in this the test case you're given, right? So this cell here, I hope you're able to see in my cursor. This
right,
particular cell here is the exit, since it's right adjacent to the boundary of the grid, right? So it means it can
right,
through this the prisoner can cross the boundary and run away.
right.
Otherwise, if this would have been blocked as well, then there would be no possible path for the prisoner to go anywhere either, right? So, but yeah, again, we have guards as well. So even though we have a path, it might be possible that a guard will be able to catch up with us in any case. And just to make it easier for you, the speed at which guards move does not matter, right?
Okay, what is the
And for
maximum dimension of this grid?
the maximum dimension of this grid can be 10 to power 4, you can assume.
10 to the 4.
Yeah.
That is, that means like the total number of cells that are present, right? So that will
Or
be
we
10
can
into
we
number.
can keep it much simpler. We can take it to 10 to power 3 as well. 10 to power 3 works. 10 to
All right.
yeah. So
One solution that comes to my mind is actually we can use a breadth first search. I think we can do a breadth first search by firstly adding all the position of the guards as well as the prisoner. We always do the prisoner at the end of the queue, and we basically propagate the guards that all the places that they could potentially go away, right? So basically they keep a visited cell array, and at each position the guard reaches, we essentially assign a wall. we replace that we replace that the cell that the guard reaches by a wall, so that way, I mean, we are like we are mixing two conditions where the prisoner basically, the wherever the guard is present, the prisoner wouldn't go there, so we can assume that it's a wall only, right? So
okay, go on.
so we can just expand every guard's premises at each turn, and we can propagate it to produce more and more walls at each step. And lastly, when its prisoner's turns for the level that we are propagating, we we do the same thing with the prisoner as well, right? And we can essentially, if we were to reach the end or the edge case, we can return yes. But if it were to be a case where the queue essentially doesn't contain any prisoner, right? We arrive at a case where the all the possible places the prisoner can go has collapsed, or there are no places the prisoner can go because he is surrounded by some walls. So that way we know that the prisoner can't reach the end.
Okay, so you're basically saying any place where a guard can go, you'll turn that into a wall, right?
Yeah.
So let's say a guard can go here, or let's say, okay, for example, this test case, I remove this wall and I make a path here, right? So this guard can go from all the way here to here as well, right? So if you turn this all of this into a wall, right, the next time the when you do a run with the prisoner, this pathway will seem blocked, but but it is possible for the
I can actually uh, visualize this too. Let's just
okay, let me
take
just
start with the case, right? So basically after the
1 second. Let me just put that back here. Cool.
right. So basically we are the first level, right? So basically we do the guards first. We turn the upside part of this to a wall. We turn the bottom part of the side with a wall, but we actually don't record this part as a wall. We actually record this as a part of the guard, right? So we actually append this back to the queue. So this becomes guard, this becomes guard, this becomes guard, and its bottom side also becomes guard. Now coming at prisoner, this becomes A, this becomes A.
Okay, why is that the cell adjacent to it is not guard? The one here, it was also empty, right? The guard could move there as well. Guard could
Where?
actually, the guard could move here as well, right? To the prisoner's
Right.
cell
Right. Yeah.
simultaneously. So we're okay. The guards are not waiting for the prisoner to move; they are moving simultaneously. So please keep that in mind. So if they were to move simultaneously, what would happen? Because let's say in this, I think this approach works if, let's say, the guards were to move first, right? Or maybe uh, prisoner has some head start, right? Let's say from
But
an instance.
in this case as well, so they are moving simultaneously, right? But if a guard is trailing a prisoner, it will never eventually reach it. If it can't achieve a shorter way, it will never actually reach it since the speed is same.
Yeah, so a shorter, okay, if this,
Even if they're adjacent, they can't catch it. I mean,
okay,
they're
let's
moving.
say if they're okay. So basically what he is saying is that, okay, please go ahead
Yeah.
with your approach and let me know, or let go on with the dry run of your approach. Then we'll have
Right. So
further discussion.
this becomes the position of guard. I think what you meant to say that firstly we are having a prisoner right here. I think this will also convert it into guard. But since in our queue array, we will also have a point to that points that this place was the prisoner place. We are not actually essentially we won't be breaking out of the loop when there is a when we potentially match each other. We will be breaking out if there is no place for the prisoner to go. Basically, we still have a place for prisoner to go, and the prisoner moves ahead. So if I were to simulate this in a more practical manner, I think all the other guards can't ever reach this guy. So basically, what would this become is the most optimal path just becomes basically the guard has moved up and the prisoner has moved right. So that is the kind of the code which our code tracks, but it eventually tracks everything because it is just moving, propagating every guard in the all possible ways, right?
Yeah.
And same ahead, I think this guard moves ahead, but the prisoner moves ahead. And since there is a wall here, they just keep on moving in this fashion, right? So they come down, and again it does that, and eventually it reaches the boundary.
Okay, and there
At
can
where
be multiple boundaries as well. But there's only one end exit point. There can be multiple exit points.
I think BFS catches it correctly because it always find the best path.
Okay, makes sense. All right, what will be the time and space complexity of this problem?
It will be a linear search only because the maximum value, as you said, that 10 power 3, so it will only be O to power n because we will essentially be propagating at each direction, but we will keep a visited index. Thus, we don't repeat indexes, so it will be time complexity will be O to power n. And for space complexity, we don't actually need any extra space. I think it's a constant space thing. Since we are actually mutating the list in its place, so the grid is mutated in its place. We don't actually need any extra pointers that helps us.
Okay,
Any data structures that help us.
okay. Now we can go ahead with this.
All right. So we actually do keep a visited array, right? So I think for the visited array, it becomes often. So the overall time space complexity also becomes
So
often.
is it O of n? What is n
I'm
here?
assuming the bigger n, so the capital N stating all the number of cells in a grid.
Okay. So in short, you want to say n into m. That's
N into m, yeah.
okay. Makes sense. Okay, so we can go ahead with this approach.
Right, so I'll just create a new file. Do I get some boilerplate code or do I just start this?
You can start with the auto boilerplate code and define a function by yourself.
All right, so
where you will be given this dimension of the grid and the grid vector is.
so I'm just given a grid, and grid is basically the grid variables point us where what is present, right?
Yeah.
So we are only given one variable, and we have to, this actually returns a string. Do I return string or do I return a bool value, true or false?
You can return a bool value.
Yeah, all right. So this, we call this bool, and all right. So how do you do that? So I think we can just start with a queue. So first of all, um, uh, we do a queue, and this queue will contain all the places wherever uh, this will contain, let makes it contain I, J, and the type of character that is present there. Right? So the type can be, we can enumerate this, it could be a enum, but we can just maintain it by 0 and 1, since there are only two characters, that is 0 for a guard and 1 for a prisoner.
So okay.
So basically, this is how we maintain that. What if the we run out of prisoner places, right? So basically, the prisoner was popped out of the queue and he didn't get appended back. So we know that we have arrived at a case where all the maybe a card have caught up to him, or is there any solution even possible or not?
Okay.
So for I in range len grid, and for j in range, actually we don't even need to go over the indices, we could just go for I in grid, and for basically for row in grid, and for cell in row. So if cell is equal to a g, that means we have encountered a guard. So we append, uh, oh, we do need ing, since we need to append cells, my bad. In range len grid, I'll do just that quickly. For row in, for call in range len grid 0, or should I say row, grid row, right? So if grid and row call is equal to g, now it's a guard, so we append a guard to it. Row dot call dot, we know that it's a guard, so we append 0 here. And uh, if grid row call is actually a prisoner, so if it were to be a prisoner, right? So basically there is only one prisoner that is given to us,
Yeah.
right? So we can actually keep this prisoner aside, since we actually do need to keep it at the end of the queue. So we only update this prisoner for in the last. And why do we do that? Because if it were to be, if a guard is present such that it will pose obstruction in the place of the prisoner in the next step, such that if a guard is present diagonally, right, and the above cells are empty, so we move the guard first, so there becomes a wall such that the prisoner can't move ahead, right? So it get popped, but it won't be appended back, such that he won't move the prisoner, right? So basically, we assign prisoner, we append draw com call, and lastly we append our uh, prisoner's value, prisoner's indices, prisoner z comma 1 comma 1. So we have arrived at a queue that contains all the guards ahead, and then lastly the prisoner.
All right.
Okay, so that's how we know we are moving a prisoner right now, or we are moving the guard. That's perfect. So we do this while queue, and we can add a check right here. So basically, if this queue's last part, so basically we can actually do this right here, and while queue, and is basically q's last value is equal 1. So basically we know that the last guy that is present at the end is basically a prisoner. So basically prisoner has been not been caught yet. So it does have positions to move around, or basically it has not congested just right now. So we do that I comma j comma t, t returns a type, we pop t, we pop the first index, we pop the first character that is present, and first of all we directions we can in, uh, initiate a new list right here that will contain all the directions, basically all the places this thing can move to, and this is pretty easy. We also maintain a visited set that will contain if the index that we are iterating right now has not been iterated before.
All
So
right.
uh, while q and q comma minus comma 1, actually I think we do need to pop everything, so we can find this just in the range for I in range len of q. So basically right now first of all we have popped the first element, and what do we do now? So basically first of all, so we are right now moving this ahead, right? So basically if I comma j uh, in visited, we can just continue, otherwise we know that it has not been visited, so we add uh, I comma j, right? So now we are moving in all four directions, right? So we just call this di and dj, and we can uh, directions, we can go in the directions, and we can call this new index new I and new j, that are given by I plus di, j plus dj. And lastly, we here is the crucial part where we check if the character that was given to us was actually a prisoner or a guard, right? So I think even before that we actually have to consider this, basically if the next index that we have come to is actually a right index, if it equals to ni, if it equals to grid, and again like for the j part, len grid n uh, ni, and grid ni nj is basically is not a wall, right? So is uh, or maybe we can just call if it's empty space, we only that we will need to do anything. So basically if t is equal to 0, that is we know that it's a guard, so we assign this space that we have a right to ni nj to a guard. I think we can just append, we don't need to actually place a wall, we can just append guard, since we are only checking for the empty spaces right here, right? So basically even if it's a guard present, the prisoner won't be able to move here, so we provide we append this to here. And basically since the guard has moved right now, so we can append this back to the queue, and else we know that the only the type is what's prisoner. So basically if we need to check uh, prisoner can escape, right? If prisoner can escape, so basically if the arrived index is either any boundary, so it could be n grid minus 1, or nj equal 0, or again nj equal n grid and I minus 1, we return true immediately. And otherwise we simply append this new index n comma nj n1, right? So we append back to it. And in case we don't ever we run out of places to move for the prisoner to move, or else case we return false. I think this should work, right?
Okay, can you quickly do a dry run on the test case given to you?
Right, sure. So I'll just paste this case right here, and first of all we maintain a queue. This queue is initialized as all the places that guards are present, so we can see that this is a length 1 2 3 4 5, and the guard is presented 1 comma 1, so this becomes 1 comma 1 comma 0, and the next part becomes 1 comma, okay, so 4 comma 1 comma 0, that's another guard, and we go to the next guard that is given by 1 2 3 2 3 4 5 2 3 4 5, yeah, that is given by 3 comma 5 comma 0, and lastly where is the prisoner right, so the prisoner is at 1 comma 5 comma 1, so we have this queue that is presented to us after this queue building thing that we do, and the visited is currently empty set, and direction says directions, and yeah, so basically first of all we pop the first thing, we get this, and now we actually add this index to the visited set right here since it was not present, and we basically in all 4 directions, right, so basically all 4 direction becomes 1 comma 2, they become 2 comma 1, they become 0 comma 1, they become 1 comma 0, so basically all cases wherever we can go, right, so but only 2 dots are present, so we turn these into guards. So these two, basically 1 comma 2 and 2 comma 1 gets turned into guards, and we repeat this process for every guard that is given to us. We pop the next guard, and we also append this new index that they have provided to us, right, so we actually append it right here, we get 1 2 1, that is 0, and we also do same thing for 2 comma 1 comma 0, so the queue keeps on expanding, and basically right now we are at 4 comma 1 comma 0, so this part becomes guard, and we add this new index to it, so this becomes 5 comma 1 comma 0, yeah, so we do this for the next part, and for this next guard this part becomes guard guard and guard, right, and we append the indices accordingly, so basically the indices become 4 comma 2 comma 0 and 2 comma 5 comma 0, as well as the bottom one, so that becomes 4 comma 5 comma 0, yeah, so after that we come to our prisoner, so we pop this prisoner, and we can see that left place is empty, so this becomes prisoner and the right part becomes prisoner, right,
Okay.
so we add another prisoner case right here, we 1 2 3 4, that is 4 comma, oh no, the row part is this one, so 1 comma 4 comma 1, and this becomes 2 comma, oh this was, yeah, so 1 comma, and this was card 1 2 3 4 5 6 6, yeah, so 6 comma guard prisoner, right, so we can see that the queue gets we again arrive at this queue where the last part is still guard, last part is still prisoner, and we repeat this process till basically the prisoners eventually walk off this case, right, so this way, and lastly when we arrive at this position we trigger this loop, this case where ni becomes len of grid -1, we return true, so the answer return is true.
Okay, all right, now that seems good. So before wrapping up, if you have anything to add, you can just say right now, and then we can move on to the review.
Yeah, I think I'm good. We can go ahead with the review.
All right. So I'm sharing the notes, interview notes with you. You can check that, open that on your screen, right?
All
So
right.
yeah, see you can already hear. So overall, I from my side, I'll say it's a lean hire from my side, right? So you will be able to progress towards the next rounds, right? And I'll tell you the reason why it's not a strong hire, because
Yeah.
for the first problem, uh, yeah, for the first problem, the actual types complexity which it could be reduced would have been O of n. The best possible answer is O of n, right? If you would have reached to that, then it would be had been fine. And there's some nitpicks here that the variables that you used could be better, right? And you did not manually test edge cases, right? And again,
Right.
if we had an optimized solution, right? I told you O of n, so
Mm.
we maybe some kind of if you would have said something along the line, okay, maybe there is a better approach, or made some kind of optimization, that would have been good as well. Overall, your DSA was good, right? You were able to convert your thoughts into the code, and you already knew concept like heap, and you're actually able to use them for this particular problem, right? And you also conveyed your thought process throughout properly. So it's a 4 on communication, and it's a it's a 3 on coding, and the speed was overall decent, right? If you had done it other less than 30 minutes mark, then it would have been let's say 4 on speed.
All right. Right.
Then we can move to the second question, right? So again, it was I really liked your approach towards solving this problem, and overall you got the highest points in towards communication, coding, and speed. For the DSS part, I gave 3.5 because you again you were not. I think you were not able to make me believe that okay, this might not run into potential edge cases, right? It discovers all test cases, but I think this approach should work, right? And again, there's
Right.
some things you missed out. For example, you did not handle the edge cases during the coding part, and did not test them at all. And uh, if there were any potential optimization, which I don't think there are, right? So that we can ignore that. But overall, it's a lean hire. Would have been strong hire if we had mostly if we had got into the O of n solution for the first problem.
Right. Yeah, that makes sense. That makes sense. Yeah, that's fair.
All right. So thank you, Rahul, for coming here, and all the best for interviews.
Yeah. Thanks, man. Cheers.